Hello to all. This is the 8th lecture of the Electronics Measurement and Instrumentation. I, Dr. Indu Prabha Singh, Professor in Department of Electronics and Communication Engineering, Shri Ram Swarup Memorial College of Engineering and Management. Today I will discuss what is the different measurement techniques of low current, low resistance, medium resistance and high resistance measurement. So, I will discuss different methods of medium resistance measurement, methods that are used for the low resistance measurement and the methods that are used for the high resistance measurement. So, medium resistance means the value of resistance and the resistance that we are using in normal days, daily purpose. Low resistance means the measurement of resistance of any wire or the coil which is used in the PMMC instrument or this. So, the value of resistance is very low, and in high resistance, suppose we want to measure the resistance of any insulator, then we will use the high resistance measurement techniques. So, yes, in low we can see that this is the measurement of different values. That means, in low resistance, when the resistance value is less than 1 ohm, then that is considered as low resistance. When the resistance value is between 1 ohm and 100 kilo ohm, then it is considered as medium resistance, and when the resistance is more than 100 kilo ohm, then it is considered as high resistance. So, these are the type of resistances, the variety of resistances or the division of the low, medium and high resistances. So, when we want to measure medium resistance, means the resistance which has a value between 1 ohm to 100 kilo ohm. So, there are many methods. So, I have written here 4 methods. So, first is the Ammeter voltmeter method, second is substitution method, third is Wheatstone bridge method and fourth one is ohm meter. So, ohm meter method I have already discussed in previous lectures. So, I will not much discuss here, because in ohm meter we directly put our resistance to the ohm meter and it will measure the value. So, I have already discussed this method of ohm meter measurement. So, here we will discuss one by one. So, first is Ammeter voltmeter method. So, simply we know that V is equal to IR. Okay. So, means if we measure voltage and current, then we can find out the value of resistance. It is very simple. So, voltage we can measure by using voltmeter and current we can measure by using ammeter. So, there are 2 methods of measuring medium resistance. So, first we will place a voltmeter in this place across the voltage which we want to measure, the circuit whose resistance we want to measure. So, we will apply the 2 terminal across that resistance. So, the voltage across that resistance is first measured by this voltmeter, and then there is we will place an ammeter and then the resistance. So, this is a voltage source and then this is a voltmeter, ammeter and the resistance. So, what will happen, suppose this is the unknown resistance whose value we want to measure. So, what will happen, the voltage across this resistance is suppose VR. So, and the current which I current that is flowing from the source is flowing through the voltmeter and this ammeter and then through the resistance. So, we will see that R1, this the value of this resistance is R1 and this is the voltage across this VA, this ammeter, this is the voltage that is the measuring this voltage, and this voltage V is equivalent to VA plus VR. So, R1 this resistance is equal to VA plus VR by I, and then VA is equal to I R1 plus IR by I. So, it is equivalent to RA plus R. So, in this instrument the relative error, that is the error is basically our main the value of resistance that we want to measure is basically R, but what we are measuring is R1. So, R1 is equal to RA plus R. It means ki there is an error of resistance that is denoted by RA. So, the error is R1 minus R by R is equal to RA by R. So, in this method if we can see if the value actual value of the resistance is R and the value shown by the instrument is R1, measuring value is R1. So, there is an error of RA. So, it means if the resistance value R is much greater than RA, then we can use this method. So, this method is very useful if resistance is slightly greater in value, because the range is 1 ohm to 100 kilo ohm. So, if we want to measure the higher value of resistance, then we will prefer this method. It means ki we will put a voltmeter in across the voltage and the ammeter after that. But if the value of resistance is low, then we will use this voltmeter method. So, in this ammeter voltmeter method, we will put ammeter we connect it with the supply voltage, and then we will put the voltmeter across the resistance. So, here we can see the current is flowing through ammeter and then voltmeter and then resistance. So, the current which is actually flowing through this ammeter is divided into two parts in IV and IR. So, here the V dash is equal to the voltage which is same at there. So, here the value of R2 is equal to the voltage V divided by the sum of these two currents. So, it is V by IV is equal to V by RB plus V by R, and this is equivalent to this one. So, here the error is basically R by RV. So, we can see if the value of resistance, since voltmeter resistance is very high, and so the resistance R, if it is low, then only the most of the current will flow through that resistance. If the value of resistance is very high, then this current is divided into two parts and we will not get the accurate value. So, this method is used when the resistance value is at lower side. So, for the higher side resistance, medium, although we are measuring the medium resistance, but if the value of medium resistance is at higher side, then this method has less error. But when the resistance is at lower side, then this method is preferred and it has low error. So, similarly, the relative error is 0 for RA is equal to 0 in first case, I have already discussed, and for the second case the error is 0 when RV is equal to infinite. So, now this equation, when we will put the relative errors of both the equation, then we have R is equal to root RA RV. So, by this formula we can define ki which method is preferred for which resistance measurement. So, hence for the resistance greater than this value, we will use first method, and if the resistance is less than this value, we will use second method. Then there is substitution method. So, in substitution method, what the unknown resistance is basically compared with the standard resistance. So, as we can show in figure, the resistance of an unknown meter, okay, we can see in figure this that what we are using an standard voltage source, then we are using an ammeter, and then first we put the standard resistance, okay. Then first we will put our resistance, and then we will note the value of this ampere meter, because the voltage this E is a standard value. So, we will read the note the value of ammeter, and then we will put the standard resistance. First we will put our resistance, unknown resistance whose value we want to measure, and then we will note down the value of voltage and the value of current. Then we will put our standard resistance, and we will vary the standard resistance till the value of current is the same, which is the for the unknown resistance. When the same value of current, because ammeter this voltmeter is same, voltage is same. So, voltage is same, then only we have to vary this resistance to get the same value of current, and then we know the value of a standard resistance. So, it means that the value of this resistance is same as the standard resistance. So, this is the substitution method. So, here we can see the value of ammeter reading is noted. Now, the switch is moved to the position 2 and SS varies in order to achieve the same ammeter reading as I have discussed. So, by this we can find out we know that R is equal to V by I. So, we can find out the value of the resistance. Then the other method is, that is very popular method, is Wheatstone bridge. So, in Wheatstone bridge method we can place the unknown resistance and 3 known standard resistance in the form of bridge. This circuit is known as bridge circuit. So, we can put, suppose our unknown resistance is suppose R1 and R2, R3, R4 are the known resistance. So, what we will do, there is a galvanometer. This galvanometer is very sensitive instrument, and very sensitive galvanometer is placed, so that if there is a difference of current is in nanoampere, then it will also deflect. So, here we use a standard voltage supply, and then we see when the voltmeter will show a 0 reading, when the voltage across, the voltage difference across these galvanometer is 0. It means the voltage at C is equivalent to the voltage at D. So, when the voltage at C and D is equal, then there is no voltage difference and no current will flow through the galvanometer. So, we can see at that time when there is voltage at this point and this point is same. So, it means I1 R1 is equivalent to I2 R2 as shown here. Okay. Then next, if we find out the value of I1, so we can see that the I1 R1 plus R3, okay, I1 is equal to I3, the same current is flowing because there is no current through the galvanometer. So, I1 is equivalent to I3, and that is equivalent to V by R1 by R3. Similarly, I2 and I4 are equal, and this is equivalent to the V by R2 plus R4. So, here we want to balance the bridge first. So, for balancing the bridge, what we have to do, we are using one variable resistance, because when we put an unknown resistance R1, then the bridge is not in balanced condition, it means it is in unbalanced condition. So, unbalanced condition means ki yes, there is a current flowing through the galvanometer. So, we will adjust by varying this R2 resistance, so that this galvanometer will show the 0. So, this type of instrument is available in the laboratory. So, we can change the value of the resistance, and here this is the galvanometer which is showing the value of the current. So, here we can see that I1 R1 is equal to this one, and if this I1 value and I2 value we will put in this equation, we will get this. So, we can see that I1, if we put I1 V, okay. So, it is I1 is equal to V by R1 plus R2. So, we can put V by R1 plus R3 is equal to, okay, I2 and R2. So, I2 is equal to, and here is R1 and here is R2 into V by this value R2 plus R4. So, by solving this we will cancel it, and then it is suppose R1 R2 plus R1 R4 is equal to R1 R2 plus R2 R3. So, this R1 R2 is cancelled out, and then we will find out this value, that R1 is equal to R2 R3 by R4. So, by this method we can measure the value of R1, that is unknown resistance. So, application of Wheatstone bridge we can use for the cable fault finding, we can use it for the measurement of the pressure, or we can use it for the measurement of temperature, and we are also using it for the rectifier circuit, the way circuits are used. We can use it for the RMS measuring instrument, as we have discussed in second lecture. So, in that also we have used the RMS, true RMS meter, we have used the Wheatstone bridge. And after modification of some, means we can change the resistance by the capacitance and inductance, and then we can measure it by the, we can measure the unknown value of capacitance and resistance also. So, what is the limitation of Wheatstone bridge? That we can't measure a very low value of resistance, because when we want to measure very low value of resistance, then the lead of that resistance is also create an error. So, the low value of resistance is not used for the measurement. So, similarly Wheatstone bridge is also not useful, not suitable for the high voltage, high resistance measurement, because the galvanometer is not much sensitive for the high resistance. And there is due to the change in temperature, due to the heating effect, sometimes the value of the resistances, standard resistances of the Wheatstone bridge is changing. So, these are the limitation of the Wheatstone bridge. So, next is the low resistance measurement. So, in low resistance measurement, first we can use the ammeter voltmeter method that I have discussed in previous slides. Then the second is the Kelvin double bridge method. So, the problem is with the Wheatstone bridge is that if the resistance is very low, suppose it is less than 1 ohm, then what will happen, the lead of the this Wheatstone bridge will also add some resistance there, and so we can't find the exact value of the low resistance. So, for low resistance measurement we are using Kelvin double bridge method. So, what is in Kelvin double bridge method? The bridge configuration is like this way. Here suppose we want to measure the resistance whose value is very low. So, how we can measure it? We can see there are two sets of arm, one with resistance P and Q and the other is small resistance P and Q. So, one arm is with capital P and Q and one arm is with small p and q, and this R is the unknown resistance whose value we want to measure and it is of very low value. This R represent the lead, the resistance of the lead, contact resistance between unknown resistance and the standard resistance. This S is the standard resistance. So, here we will make the P by Q, capital P by Q is equal to small p by Q, and then the bridge will we will balance the bridge and we will get the output. So, what is here? Suppose first thing that we will measure the voltage across E and D here. So, here is the voltage, means the total voltage from here to A to B is basically E volt. So, we want to measure the voltage across A to D. So, voltage across A to D, what will happen? We will apply a voltage divider rule. So, the voltage divider rules means the voltage across P we want to measure and the total voltage is across P and Q. So, by voltage divider rule it is P by P plus Q into EAB, this voltage across E and B. Then and what is EAB? We have to measure the voltage across this. So, what is E and B? Voltage across E and B is basically this R voltage, the resistance current I into total resistance, and total resistance is basically R plus S, these two resistance, and then this small resistance R. So, this small resistance we can see the current that is flowing through this R, then it will flow through this circuit and it will also flow through this circuit. So, it means that this R is in parallel to the series combination of P and Q. So, same we have applied here, that is P plus Q into R by P plus Q plus R. So, this is the resistance. So, again in this the EAD is equivalent to EAMC, same voltage. So, what we will put the value of EAD we have calculated in previous slide. So, it is P by P plus Q into AB. Now, the EAMC. So, EAMC, AM and then C. So, we have to find out this voltage. Okay. So, this voltage is because this voltage is equivalent to the voltage across A and D, because both are in parallel, because when the bridge is in balance condition. So, here we see that this R is there, but the value of resistance we have calculated R, and this value of resistance now we have to calculate this. So, it means that this P is in parallel to this Q and R. So, it will be P, we are applying the voltage divider rule. So, R value we know and the value of Q this voltage across P we have to find out. So, P by P plus Q into this one, this is taken from the previous slide. So, now this is equivalent resistance. Now, when we solve this equation 1 and 2, and then we will put the after expanding these equation, there is a term that is P by Q, capital P by capital Q minus small p by small q. So, when we will put capital P by Q is equivalent to small p by Q, then we will find out R is equal to P by Q into S. So, under the balance condition, here the contact resistance is completely eliminated. So, the error is 0. So, by this method we can use a very low value of resistance. Suppose we want to measure this resistance very accurately also, then we have to reverse the battery position, and then again we have to calculate the resistance value by same formula, and then we will take the average of both the resistance measured value, and that will give the accurate value of the resistance. So, this circuit is very useful for the low value of resistance, that is the resistance whose value is approximately 0.1 micro ohm to 1 ohm. So, very low value of resistance can be measured by this method very accurately. So, there is high resistance methods. So, high resistance can be measured by first the loss of charge method, means we have to charge a capacitor by this resistance, and then we discharge this capacitor, and then that will give the total the loss in charge. By this formula we can calculate the value of resistance. Next one, there is one meter that is known as Megohm meter, that is used for the measurement of high resistance, and then there is a Megohm Bridge method, and one more is the direct deflection method. So, for the high resistance we have some problems, that is the problem of electrostatic charge that can be accumulated on measuring instrument, and the second is the leakage current become comparable to the measuring current, and that can cause error. So, we will first discuss the loss of charge method. So, as shown in figure, there is a switch S1 and S2, and there is unknown resistance Rx. So, the first step is what we will do, there is an electronic voltmeter, electrostatic voltmeter V is placed and the unknown resistance Rx is placed. So, first we will switch on the S1 switch, means we will put the S1 switch close, and then we will leave the capacitor to charge. Then the capacitor is charged for a certain period of time, then we will open switch S1 and we will close the switch S2. Then this capacitor will discharge through Rx, and it will also discharge through this R leakage, means the voltmeter and the battery, whatever the path it will give, it will find, it will also discharge through this. So, the total resistance that we have to measure is the 1 by R equivalent is equal to 1 by Rx plus 1 by R leakage. So, if we reduce the value of R leakage very low, then we will find out the value of Rx. So, we know the discharging equation of the capacitor is equal to V is equal to V1 e to the power minus t by C R equivalent. So, this is the discharging capacitance. So, we can measure the Rx value of resistance, the unknown value of resistance. Similarly, in Megohm bridge method, we can use a simple bridge method by for measuring the high value of resistance. But in high value of resistance, because there is a guard terminals there, suppose this is the main resistance R, then there are two resistances also leakage resistance that is produced, that is RAG and RBG. So, what will happen when we measure it by a Wheatstone bridge? So, suppose this resistance is having 1 kilo ohm value, 100 kilo ohm value. So, that if it is having 100 kilo ohm value, then it will show only 68 kilo ohm or like that. It means when we are using high value of resistance with normal bridge, it will give an error of more than 33%. So, for this method we for this measurement of high value of resistance, we are using Megohm bridge method. So, what we are doing, we are using this this resistance and the leakage resistance, the guard resistance, we have to connect with the this galvanometers parallel. So, there is no current flow through the guard resistances, and this will give the accurate value, and this R is equal to P s by Q. Similarly, Megohm is an instrument and it simply measure the value of resistance. Previously the resistance is used with the handle, and when we change the handle, this will measure the electronic Megohm, but now the Megohms are available that can directly measure the value of the resistance. So, we can read the value of resistance directly by using Megohms. Now, direct deflection method. In direct deflection method, what we are doing, suppose we want to measure the resistance of this insulating material. So, we have core material, that is the conducting layer, and there is an insulating layer, and this is the metallic sheet of this over this. So, we want to measure the resistance of this insulating material. So, what we will do, we will have a galvanometer, and we will put one terminal of this with this insulating material, and the positive terminal is connected with the galvanometer, and the negative terminal is connected with the metal sheet. So, between this core and the metal sheet, we can find out what is the resistance between these two, that is the resistance of the guard wire, that is the resistance of the insulating material. So, this gives the direct deflection. So, very sensitive high resistance which has the value of more than 1 kilo ohm or the value of more than 100 kilo ohm, we can use this PMMC instrument. So, PMMC instrument is connected in series with the resistance and to the battery, and the deflection of galvanometer gives the resistance value. Here what we do, actually it is giving the value of voltage across that insulator, but we can calibrate our instrument in such a way that it will deflect to the resistance value. So, this method is mainly used for the insulation resistance. So, the galvanometer measures the current IR between conductor core and the metal sheet. The leakage current IL over the surface of insulating material is carried by the guard wire wound on the insulator and does not flow through the galvanometer. So, it means because there is an insulator and leakage current is very low, so we can directly measure the voltage by using this method. So, this is the direct deflection method. So, in here we have discussed the measurement techniques for the low resistance measurement, high resistance measurement and medium resistance measurement. So, in low resistance measurement, we need a Kelvin double bridge. For the high resistance measurement, we have a an instrument Megohm that is known as, and directly that we can measure this. Suppose we want to measure the resistance of an insulator, then we will use a direct deflection method. For the medium resistance measurement, we are having digital multimeter circuits and other instruments. So, we can measure by that. We can use a Wheatstone bridge for the measurement of medium resistance. Thank you from my side.